Hello everyone, this is Dr. Tasadduk Hussain with one of the revolutionary and amazing equations that was put forward by Schrodinger in 1926. This equation forms the basis of quantum mechanics. This lecture has 4 sections. So the first section will be Introduction to the equation, wherein I will introduce you to the Schrodinger equation. Secondly, we will look at the derivation of equation and the different forms of equation. Thirdly, we will solve the equation or Schrodinger's wave equation in Cartesian and polar coordinates for one electron species or hydrogen-like atoms. And finally, we'll go through the significance of the Schrodinger's wave equation. First of all, we will have the introduction to equation of Schrodinger. Classical mechanics, which was based on Newtonian laws of motion, fails when applied to the microscopic objects like electrons, atoms, etc. This is mainly because of the fact that the classical mechanics ignores the concept of dual behavior of matter and the uncertainty principle. So if we say classical mechanics ignores dual behavior and uncertainty. The branch of science that takes into account the dual behavior of matter is called as the quantum mechanics. It's also called as wave mechanics. We have seen that according to de Broglie's equation, electron has a dual character, that's electron behaves as a material particle and as a wave. In 1926, Erwin Schrödinger, who was an Austrian physicist, said that if an electron behaves as a wave, there must be a wave equation which should be able to describe the wave motion of the electron. Schrödinger proposed that since an electron behaves as a wave, it should obey the same equation of motion which all other known types of waves obey. On the basis of this simple idea, he derived an equation which describes the wave motion of an electron wave propagating in 3 dimensions, x, y, and z. This wave equation is called Schrödinger's wave equation. The equation can be written in many different forms. The equation that I have written here is the Schrödinger's wave equation. I can write this equation in another forms also. So if I put these del square side where by del x square, so I'll separate these del square and the del x square regions, and I'll keep this psi common in all of them. So this equation becomes, or in other words, this equation, the equation that I have separated, I can represent this with del square. Okay, and when I represent this region with the del square, then del square and the psi is there, del square psi becomes like this, and then rest of the equation divided by h square e minus v psi becomes equal to 0 again. This region is always equal to the del square, and this del square is called as Laplacian mathematical operator. So in mathematics, for example, you do the integration, you can do the differentiation, or you can write this under root. So these are all actually mathematical operators, and this mathematical operator is always accompanied by any mathematical quantity or a numerical value on which this mathematical function becomes operative. So as an example, I'll take, for example, if 2 is a numerical number and then I'm operating this 2 with a mathematical operator under root, then in that case, when this operator under root acts on the numerical number 2, that is called as the mathematical operator. So this under root here is a mathematical operator. In a similar manner, this Laplacian mathematical operator is a kind of mathematical operator del square psi. In that case, it should not be confused with that this del square is multiplied with the psi. So what it is then? It's actually the mathematical operator that is acting on this wave function psi. So psi here is a wave function. So if I write psi, psi is a wave function. This psi actually gives the amplitude function of space coordinates x, y, z. So if there are space coordinates x, y, and z, in that case, so if this is x, this is y, and this is z, in space, this psi gives the amplitude, it's an amplitude function of these 3 coordinates x, y, and z. So for simplicity, sometimes we write psi only, but in actual scenario it's psi x, y and z, so the coordinates have to be always defined in that case. Also, these regions that I have shown here, these are the double differentiations of this psi or wave function. This is called as the double differentiation of psi. So in other words, I can say this psi, this del square divided by del x square, it's a double differentiation of this wave function psi. And in each case, for example, in this case, I'll divide this into different sections. In each case, what is happening is this is a double differentiation of x when y and z are constant. So in this case, y and z coordinates are constant. Similarly, in case of the double differentiation of y square, the x and z are constant. And then in case of the double differentiation of z square, the x and y coordinates are to be kept constant. And in this equation, when you see m is the mass of an electron, and h is the Planck's constant, and this E is the energy. It's actually the total energy. The total energy is the sum of the kinetic energy and the potential energy. This V here represents the potential energy, and E represents the total energy. And total energy E is always equal to the sum of kinetic energy plus potential energy that is represented with V. And all of this is always equal to 0. Now the second part is the derivation of the Schrodinger's wave equation. When we try to derive the Schrodinger's wave equation, Schrodinger assumed that an electronic waves which are present in an electron, they are similar to the stationary waves as I've shown here. The stationary waves which are produced by the vibrations of a stretched string. So if we consider that electron has a wave which has an amplitude of psi. Next, if x is the displacement of that wave, in x direction and lambda is the wavelength, then we can solve this psi or the amplitude by using the following equation. So herein you are considering the wave of an electron. This is an electronic wave which has a displacement x from the nucleus, wherein we take the coordinates as 0, 0, 0. So the amplitude of an electron or electron wave with respect to the nucleus having a displacement of x and wavelength lambda, in that scenario psi becomes equal to a sine 2 pi x by lambda. On differentiating this equation, so let's label this as equation 1. When I try to differentiate this equation, then I can write differentiating this equation with respect to only one coordinate, because we know coordinates are x, y and z. First we will solve this equation for the x coordinate, then for y, and then for z. So if I try to solve this equation for the x coordinate only, then del psi divided by del x, upon differentiating this equation, becomes sine 2 pi x by lambda becomes cos 2 pi x by lambda, and we will have to multiply it with 2 pi by lambda again. And upon solving this equation, in other words, we can say del psi by del x becomes equal to this 2 pi lambda and a. I will keep this with this equation, with this region, so it becomes 2 pi a divided by lambda, and this region I will keep separate, that becomes cos 2 pi x by lambda, and we'll call this as equation 2. Upon differentiating again this equation 2, what we will get is, we'll get del square psi divided by del x square, and the squaring will be on this side also. So this becomes, when I try to solve this equation again on this side, this equation becomes equal to, this is 4 pi x, that becomes minus 4 pi by lambda square, and then this a I'll keep with the sign, so a sine 2 pi x by lambda. Or in other words, we can simplify this equation further. This can simply be written as minus 4 pi square by lambda square psi. Okay, why? Because this a sine 2 pi x by lambda from the top equation you can see is equal to psi. So this we will label as equation 3. This is equation for an electron wave, one dimension, that's for the x coordinate. When I similarly try to solve this equation for the y coordinate and then for the z coordinate, this equation third will be converted into a different equation. The equation that we got is the equation 3, and we solved this equation for the x dimension of the electron wave in x axis only. Now when I extend this equation to the 3 dimensions, in that case what I can do is I can replace this del square psi divided by del x square into all the 3 dimensions. So when I extend this x square del square psi divided by del x square into 3 dimensions, this gets converted into del square psi divided by del x square plus the second dimension, that's del square psi divided by del y square, that's the y axis, and then del square psi divided by del z square. Okay, so these are the 3 dimensions that I extended this equation into. And then on the right hand side we have 4 pi square by lambda square. So this is the same equation. The only difference is that this equation 4 is in x, y, z dimension. Again, from de Broglie's law, we know that lambda is always equal to h by mv. So if I introduce the value of lambda from de Broglie's equation into the Schrödinger's wave equation, then this equation becomes, again from the left hand side it's going to be same, and on the right hand side it will be m square v square divided by h square. Okay, so this equation, we will call this equation as equation 5. This equation that I have shown here is a wave equation which actually describes the motion of an electron in all the 3 dimensions. And when the motion of an electron has to be considered in one direction only, then this equation holds there. But now since we know that an electron revolves around the nucleus in a 3-dimensional space, so this wave is going to be somewhere on the z-axis also, it's going to be somewhere on the y-axis also. So that's why we have to extend this equation into 3 different dimensions, x, y and z. In order to make it more clear, I wrote the equation here. Again, from our previous lectures, we know that the total energy of electron is always the sum of its kinetic energy and the potential energy. So kinetic energy and the potential energy, which is represented by V. So if I write it here, I can say that the energy of an electron E is always equal to the sum of kinetic energy plus the potential energy. This equation can be simplified and written as, if I transpose the terms, then this half of mv square becomes equal to E, this V comes here, then E minus V. Or I can keep this V square here, then this equation becomes, when I substitute the value of V square in this equation 5 that we derived earlier, this equation becomes minus 4 pi square psi m square divided by h square multiplied by twice E minus V divided by m. So this happens when I replace the values of V square in this equation 5. Now trying to further solve it, so left hand side is going to be same. On the right hand side, what happens is this region will try to solve. What happens is this 1m and this m square cancels out, then the right hand side becomes equal to, this is the equation that we got when we substituted the value of V square in our equation 5. Now again, if I take these terms on the left hand side, then this equation becomes del square psi divided by del y square plus del square psi divided by del z square and when this term is transposed to the left hand side, this will turn into a positive sign plus 8 pi square m by h square, and this e minus v psi is there, and everything is going to be equal to 0. Now I'll keep these operators separately and separate this wave function from there. So the operation del square del x square plus del square divided by del y square plus del square divided by del z square will be kept separately, and this psi is a common in all of them, so I separated it, plus 8 pi square m by h square e minus v psi is equal to 0. Now from our earlier discussion, I have already told you that this operator can be separately written as the del, or this we call as the Laplacian operator. So when I replace this region with this Laplacian operator, it becomes del psi plus 8 pi square m by h square e minus v psi is equal to 0. This is one of the forms of Schrödinger's wave equation. So we can write it as, this is form 1. This equation can be written in this way also. One of the forms of equation, form first, I have already shown. From our earlier derivation, we saw this equation there also, wherein we replaced this region with the mathematical operator or the Laplacian mathematical operator. Now instead of replacing this region with the Laplacian mathematical operator, instead if I multiply both sides of this equation by minus h square by 8 pi square m. So when I multiply both sides, this equation turns into, or we can say that this minus h square by 8 pi square m into this operator del square plus del square by del x square, del y square, del z square multiplied with the psi minus this I can solve. So if I multiply this wave function with e and v separately, then this becomes e psi minus and minus becomes plus, so it becomes, or if I transport this e psi towards the right side of this equation, then this equation becomes, the left hand side remains the same plus v psi, and on the right hand side we'll get the v e psi. So what I did is I transposed the e psi term towards the right hand side of the equation, and v psi I kept on the left hand side. Now what we can do is we can write that this minus h square by 8 pi square m into this operator del square, and this psi I will take common, and then v I will be here, and this is actually the addition of v, that is plus v, and psi I am keeping common. So for all of this equation, psi is common, and on the right hand side e psi remains the same. Now this region can be replaced with the Laplacian mathematical operator, so this equation becomes minus h square divided by 8 pi square m, and instead of this region I can write the Laplacian operator, that is del square, because everywhere there is squaring, or the second differential that we are looking at, and then this v stays there, and whole of this region is multiplied by psi becomes equal to e psi. Now this whole region here, it can be replaced with another operator that we call as the Hamiltonian operator, which is represented by h. Then this equation becomes equal to, here I am showing it, so this equation becomes equal to the Hamiltonian operator by h cap psi becomes equal to e psi, wherein h is equal to this operation and e remains the same. So this is also one of the forms of the Schrodinger wave equation, so we call it as form second of the equation. One of the important things that you should note here is that this Hamiltonian operator that we wrote here, this Hamiltonian operator has two important different parts. One is the V, and V is the potential energy. So that means this Hamiltonian operator has two parts. One is the potential energy part, and the second is the kinetic energy part. So potential energy part is represented by this V, and the kinetic energy part is represented by minus h square by 8 pi square m into the Laplacian operator. So this region is the kinetic energy and this V is the potential energy. Next in our lecture we are going to see how this Schrodinger's wave equation can be used in Cartesian and polar coordinates for solving the one electron species or hydrogen atom like species. So if we divide this into two parts, one is the Cartesian coordinate and the other one is the polar coordinate. So the Cartesian coordinate is basically one set of coordinates for any given point x, y and z, while as polar coordinates is defined as the infinite number of coordinates for any given point, and the polar coordinates are r, theta and psi. R, theta and psi. This r, theta and psi, whereas the Cartesian coordinates are x, y and z. First we will solve this equation for the Cartesian coordinates for an hydrogen atom. We know that in case of hydrogen atom there is only one electron that is revolving around the nucleus, and let's represent the charge of that electron by minus e. So this is charge of electron. Similarly, the charge on nucleus is going to be plus e, that is the charge on nucleus, and r is the distance between the two. The potential energy that is associated with this electron in hydrogen atom, is always going to be equal to the product of these two charges. So the potential energy V is going to be equal to the product of minus E and plus E divided by the distance, or this V is going to be equal to minus E square divided by R. That means V is equal to minus E square divided by R. Now for Cartesian coordinates, if I solve the Schrodinger wave equation, wherein I'll be substituting the values of V in the Schrodinger wave equation, then this equation becomes del square divided by del x square plus del by del y square plus del by del z square into psi plus 8 pi square m divided by h square, and this region here is E plus, and the value of V is E square by R psi equals 0. So this equation becomes the equation for hydrogen atom for this one electron species in Cartesian coordinates. In this equation, the wave function psi, it's a function of x, y and z. So this psi is function of x, y and z coordinates. Similarly, when we try to solve this wave equation in polar coordinates, wherein we'll be using this theta and this psi and the distance between these two, that's r, then in that case what happens is this, for polar coordinates, the values of this z, that is the Cartesian coordinates x and y. So first I will have to look at the polar coordinates which I can solve for the Cartesian coordinates. The Cartesian coordinates are x, y and z axes, these three axes. So in polar coordinates the z becomes equal to r cos theta. So the z is actually equal to the r cos theta, and similarly the y becomes equal to r sin theta sin psi, and when I try to solve it for the x, it becomes r sin theta cos psi. Okay, so now I solved these Cartesian coordinates into the polar coordinates, and when I try to put the values of this x, y, z in the Schrodinger wave equation, then the Schrodinger wave equation in polar coordinates gets converted into the same equation here. This gets converted into, in case of the polar coordinates, this wave function psi is a function of the polar coordinates, and polar coordinates are r, theta and psi. Okay, these three. Now the Schrodinger wave equation can be utilized in several ways. We can use this equation to find the probability of an electron around the nucleus. Now moving towards the application part of the Schrodinger's wave equation. Schrodinger's wave equation shows all of the wave-like properties of matter and was one of the greatest achievements of the 20th century. It's used in physics and most of the chemistry to deal with problems about the atomic structure of matter. It's an extremely powerful mathematical tool and the whole basis of wave mechanics. So whole of the wave mechanics is based on Schrodinger's wave equation. By using this equation, we can actually know how atomic orbitals look and what is the shape of different orbitals like s, p, d and f orbitals. Also, the Schrodinger's wave equation can be used to know about the behavior of particles in a field. I think this pretty much concludes the Schrodinger's wave equation, and in our next lecture we are going to deal with the atomic orbitals and how we can use this Schrodinger's wave equation in deriving the shape of different atomic orbitals. Till then, take care of yourself and subscribe to our channel if you like what we are doing here. Thank you.